This is where we stopped last time, this example, where x and y are jointly uniform on a circle of radius r centered at the origin. The question is to compute the marginal PDFs of x and y and the expectations, as well as the expectation of the product xy. Okay, so the setup is very simple. The joint PDF fxy of xy is a constant inside the circle. So it's equal to c if x and y belong to the circle of radius r. In other words, x squared plus y squared is less than or equal to r squared, right? And 0 otherwise. Okay. First thing is to determine c. What is c? Well, obviously, the integral of fxy, xy, dx, dy on the whole real plane has to be equal to 1. Why? Because fxy is a probability density, and this integral gives us the probability that the random variables x and y take values somewhere in R2, the real plane. Okay? But that's an event of probability 1. Therefore, well, what is this integral? This integral is c times the area of the circle, right? Area of the circle with radius r. Therefore, c must be equal exactly to the area of the circle, which is 1 over, 1 over the area of the circle, which is 1 over pi r squared. Right? Now, what are we asked to find? We are asked to find the marginals, the marginal PDFs of x and y. So let's fix an x. For example, let's consider this x right here. Okay? When we consider this x, the probability density at that point is coming from an integral along y of the joint density. As you can see, depending on the point x, the value of x we choose, the area, the interval over which we integrate changes. Now, intuitively, which points do you think have higher values of marginal PDF of x? Central points, right? Here we collect more probability. Okay? As we go away from the center, okay, we're collecting less and less probability. Let's see this mathematically. Okay, fx of x, remember the marginal can be found by integrating the joint PDF over y from negative infinity to infinity in general, okay? fxy, xy, dy. This is a general result, valid for every joint PDF. Now, in our particular case, if we fix a value of x, this means fxy is non-zero only as y varies from this point to this point. What is the value of this point? What's the value of y at this point? If this is x0, this is the square root of r squared minus x0 squared, negative square root, the y coordinate here. And the y coordinate here is the positive square root of r squared minus x0 squared. Positive r squared minus x0 squared. Okay? Now, so fxy is non-zero only in the interval from negative r squared minus x squared to positive r squared minus x squared. And inside that interval, the value of the PDF is fixed at 1 over pi r squared. This integral is extremely simple and evaluates to be 2 times square root r squared minus x squared divided by pi r squared. As expected, this is only a function of x. It's a function of x tells us something more about the PDF of x. Originally, the PDF was a constant in a given region. It's not a function of either x or y. It's a uniform distribution. Okay? If you look at this, the marginal distribution of x, do you see the difference? Here, this PDF is a function of x. It's not a constant, so it's not a uniform distribution. Originally, x and y were jointly uniform. Marginally, they're not uniform, which is what we expected, because we expected the center to be more likely in terms of x, and the edges to be less likely. And if you plotted this, I can't plot this exactly right now, but at least I can give you an idea. We can all get an idea of how it should look, at least where is it 0. At the edges, negative r and r, this is 0, right? As we expected. Where does it make a maximum? Where does it peak? At 0, right. So it could look like this, for example. Oh, mine is a little asymmetrical. Okay, how about this? Maybe. At least it makes, it increases as we approach the center. Okay, how about the marginal PDF of y? Fy of y. By total symmetry, it's going to be exactly this, except we, replace x by small y, script y. Well, let's write that for completeness. It's the integral as x goes from negative square root of r squared minus y squared to the positive square root r squared minus y squared, 1 over pi r squared dx, which is 2 times square root of r squared minus y squared over pi r squared, as long as y in absolute value is less than or equal to r and 0 otherwise. Okay. Maybe we should write the range here as well, because we omitted it here. Fx of x is equal to this, provided the magnitude of x is less than or equal to r, and fx of x is 0 otherwise. Any questions? Okay, now we are asked to find the expected value of x and y. That's going to be easy, provided we know the definition of expectation, which is x times fx of x dx from negative infinity to positive infinity in general, right? Okay, we have this marginal now. We've just computed it. So the integral, in fact, only goes from negative r to r. And inside negative r to r, the value of the PDF is given by 2 times square root r squared minus x squared divided by pi r squared dx. Now you may think this maybe it's not such a trivial integral. However, if you look closely, this is an even function, which makes the whole thing, x is an odd function, which makes the whole thing an odd function, right? So, and we are integrating in a region that's symmetric around the origin. So the integral is going to go to 0. Explicitly, you can split the integral into two pieces. 2 over pi r squared x square root r squared minus x squared dx, plus from 0 to r, 2 over pi r squared x square root r squared minus x squared dx, and this part will cancel each other. So we get 0, which is pretty obvious to start with. Why? Because if you look at this joint distribution, x is exactly as likely to be to the right-hand side of the x equals 0 line as it is to be on the left. Okay? There is exactly the same amount of probability on the right-hand side of the origin as there is on the left. Same situation for y. It's completely symmetric. We can easily write by symmetry that the expectation of y is 0 as well. How about the expectation of x times y? Let's write it the long way. Maybe I'm going to erase some part of here. Let's write down the expectation of x times y. This is a multiplication. Sometimes when we say fxy of xy, we write x and y side by side. I know some people confuse this with multiplication. This is not a multiplication. This is just a notation of joint PDF. This, however, is a real multiplication. Expectation of x times y. How would you do this in general? In general, take a double integral of xy, x times y, times the joint PDF over all x and y. But in our case, this is simply, well, suppose x goes from negative r to r. As x goes from negative r to r, y goes from negative square root, right, of r squared minus x squared to the positive square root of r squared minus x squared. Xy times a constant, 1 over pi r squared, dx dy. Well, clearly, you can show in 1 or 2 more steps that this is 0. So, what did we find? In this example, the expectation of xy is 0. The expectation of x is 0. The expectation of y is 0. So incidentally, the expected value of xy is equal to the expected value of x times the expected value of y in this example. It's not our current topic, but I'd like to stop here for a second because I know that in EE 306 this comes up a lot, and some people still continue to be confused after this class. So let's stop here for a while and think what this means for us. Expected value of xy equals expected x times expected y in this example. This is not true in general, is it? No, doesn't have to be true at all. But it's true in this example. What does this tell you about these two random variables?
They're not related.
They are? It doesn't tell us that they're independent. So this is... they're uncorrelated. Remember, we did this in the joint PMF case. So they are, X and Y are uncorrelated. Uncorrelated. Formally, we'll define the correlation coefficient, etc. later on. But, you know, in this example, it's worthwhile spending a minute on this. How about, are they independent or dependent, do you think? They are, in this case, dependent. How do we understand that? Well, it's sufficient to look at this picture and fix a value of x. When you fix a value of x here at x sub 0, for example, the range of y goes from this value to this value. However, when x is at this, here at 0, y goes from negative r to r. So the distribution of y depends on, the conditional distribution of y depends on x. Okay? We'll formally define independence toward the end of this hour or the next hour. Okay. Now that we said conditioning, let's define conditional PDF of one random variable conditioned on another. Okay, let x and y be two random variables with the joint PDF fxy. For any y with positive density, fy of y, the conditional PDF of x, given that y is fixed at value script y, is defined by fx given y equals fxy divided by fy of y. Okay, so just like we do in PMFs, we find the marginal density by dividing the joint density by the, we find the conditional density by defining the joint by the marginal. Okay. You may say, well, these are not probabilities, so why are we dividing them? And you may also ask the following. Y is a fixed value and the random variable capital Y is a continuous random variable. So the probability that Y takes on this particular value is 0. So how can we condition on an event with 0 probability? Okay? But notice that we are not finding a probability here. We're just finding a density function. Okay? And the fact that the probability of y being equal to the particular value script y is 0 doesn't mean the event y equals script y cannot happen. Okay, it's a legitimate event. So, I think this is best understood if we, use our intuitive notion of PDFs as a probability per unit area or probability per unit length. So the probability that x is in a neighborhood of the value a and at this, given that y is in a neighborhood of the point b. This is a probability, and we understand this. Okay, think of the real plane and take an A and a B. This is A to A plus delta 1, and this is B to B plus delta 2. What do we get here? We get a certain small rectangle. Now, this is a legitimate probability. Now, what we do next is also legitimate, and it follows from the definition of conditional probability, which is divide the joint by this. So basically, this is the probability that x is in A to A plus delta 1, and y is in B to B plus delta 2, divided by the probability that y is between B and B plus delta 2. No problem here so far. What we do next is sort of an approximation. What we'll do is we'll take this numerator here, and we realize that this is nothing but the probability that x and y take values in this rectangle. But then we'll approximate that probability, assuming that delta 1 and delta 2 are so small that the surface of the joint PDF does not change much over that rectangle, by simply the area of the rectangle times the value of the joint PDF at this point AB. Okay? So fxy A comma B times delta 1 delta 2. Delta 1 times delta 2 is the area of the rectangle, and this is the value of the joint PDF at this point, and we sort of make the approximation, and that doesn't change much over the rectangle. Same Riemann integral type argument. As you make delta 1 and delta 2 approach 0, this is going to become exact, so no problem. So now do the denominator. Similarly, the denominator is roughly fy of b times delta 2. Nice thing is now the delta 2's cancel, and we get fxy a comma b divided by fy of b. Remember, what was this? This was an approximation for this probability, conditional probability. That conditional probability we can similarly approximate by assume there is a conditional PDF, f x given y, a given b. Then this conditional probability would be exactly this conditional PDF multiplied by delta 1. Okay? So that makes this, and let me not forget my delta 1 here. That makes this approximately equal to this. In fact, this is not really an approximation anymore. This is a definition, which makes a lot of sense. So we define f x given y, x given y as fxy xy divided by fy of y, and the reasoning behind this definition is this argument right here. So let's compute the let's compute the conditional PDFs in our circular example. Returning to our circular example of the circle with radius r centered at the origin, fixing a value of y. Okay, let's fix it at here, for example, y0. Let's compute f x given y, x given y0. If y is at y0, what is the conditional density of x? Let's use our definition right here. By the way, this definition is only valid whenever Fy of y is different from 0, of course. So we took a point where the density of y is not 0. Obviously, here it won't be 0. So we divide the joint by the marginal. Do we remember the joint? The joint density was just a constant, which was the area, 1 over the area of the circle. So 1 over pi r squared. How about the marginal? The marginal was, it was, let's see, I don't have it anymore on the board, so you have to tell me.
2 square root.
2
Square root.
Square root
R squared
minus y squared by
P r squared.
Right, very nice. So the pi r squareds cancel. We have 1 over 2 square root r squared minus y squared. Okay. As expected, in this case y is y0, of course. As expected, the conditional density of x given y depends on the value of y. And but let's see, it has no x dependence. This is interesting. It has no x dependence, so what is this a function of? This is a function of x. It's a function of x. When we want to plot this conditional density, we need to plot it with respect to the first argument here. This is the variable. This is just the given. Okay? So f x given y, x given y is nothing but a constant with respect to x. What is the range of this in terms of x? Well, this is true as long as x in magnitude is less than or equal to square root of, right, r squared minus y0 squared, and 0 otherwise. So if we want to plot the conditional, it's going to be symmetric around the origin. And it's going to be fixed at a value which is 1 over 2 square root r squared minus y squared. Okay? As long as x is between the negative square root of r squared minus y squared and the positive square root of r squared minus y squared. So, conditionally, x is uniform. Once we know that y is fixed at this value, x is uniformly distributed in this range. In this range. Which makes sense because of the uniformness of the original joint PDF. Okay? What else? This conditional distribution depends on y. Okay? For example, if we set y to be equal to 0, let's plot that. F x given y, x given 0. Now, x will take values from negative r to positive r. And the height of the density will be simply 1 over 2r. So, fx given y changes with depending on y. If you remember the definition of independence from discrete random variables, an equivalent definition of independence was the conditional distribution fx given y, px given y in that case, would be equal to px of x, the marginal. This is not the case here. Okay? So we sort of sense that they're not independent, and we didn't expect them to be independent anyway. Right. So for completeness, maybe we should write the conditional density of y given x. Let's write that here. F y given x, y given x. What do you think? Fix a value of x this time. Here, for example. Same thing, completely symmetric. It's equal to 1 over 2 square root of r squared minus x squared, as long as y is less than or equal to the square root of r squared minus x squared, and 0 otherwise. So, f y given x, when we plot it, it's a uniform density from square root of r squared minus x squared to the positive square root. Okay? Any questions? Yes, please.
Yani biz bir bildikten sonra geri kalan daireyle işimiz kalmıyor. Sadece line ile ilgileniyoruz. Bir şey oluyor. Yani y'yi fixlediğimiz zaman sadece bir tane line kalıyor. O line'ın üzerinde uniform distribution olduğu için bir direkt line uzunluğunu da yazabiliriz onu.
Exactly. Right. The reason for that, but you can't do that in every case. If, for example, the joint density was not uniform, for example, it's twice as big on the left-hand side of the origin as it is on the right-hand side, then it wouldn't be the case, right? I suggest you do examples by, exercise on your own by changing this joint density, setting it to something else. For example, the one I just suggested, this part could be twice as high as this. Remember, we're thinking in 3 dimensions, and the joint PDF is a surface on the 3rd dimension here. Okay? So, okay, let's do another example. We have 2 examples in this topic coming from the world of fantasy fiction. Oh, not yet. First, yes, this is the one. The speed of Iron Man flying past an air traffic radar is modeled as an exponentially distributed random variable with mean 200 kilometers per hour. Pretty fast. The radar sensor will measure the speed of any target with an additive error. The error is modeled as a zero mean normal with a standard deviation equal to 1/10 of the speed of the target. What is the joint PDF of the actual speed and the error? So, let's see. What are our 2 random variables here? One is the speed of Iron Man. Okay, so that is, let's call that S. S is the speed, and it is exponential with mean 200 kilometers per hour. The exponential random variable, as we know, has a parameter lambda, and lambda is equal to 1 over the mean. So lambda, in this case, the rate of the exponential, is 1 over 200, okay, hour per kilometer. What's next? The second random variable, whose joint distribution with this that we're asked to inquire, is the error. The error let's call it n, maybe, is normal with mean 0 and standard deviation equal to 1/10 of the speed of the target. So we are not directly given the variance of the error because the variance of the error is not fixed. This is actually quite realistic with radar sensors, that the error is a function of the speed of the target you're trying to sense. So what do we know? We don't know the marginal distribution of the error, but we know the conditional distribution of the error, right? So given S equals A, okay, and maybe we shouldn't have called it N. Let's call it E, because it's going to be confused by the normal. So E is distributed as a normal with mean 0 and variance A 1/10 of the speed of the target is the standard deviation. So A over 10 is the standard deviation. A over 10 squared must be the variance. Okay. What does this mean? This means that F E given S, error given the speed of, let's say, B given A is equal to, I'm using different letters just to make sure you're not tied to this notation with capital X, small x, capital Y, small y thing. Okay? So what is this? The conditional distribution of E is normal. Do you remember the normal? 1 over square root 2 pi sigma squared. In this case, let's put A over 10 outside the radical. E to the power negative B minus the mean, which is 0, squared divided by 2 times sigma squared. A over 10 squared. Okay. So we have been given in the wording of the problem this as a fact. All we have to do is write down the joint PDF, which follows from the definition. Fe given S, B given A. What did we define this as? We define this as the joint divided by the marginal. Right? Therefore, the joint can be found by cross-multiplying these two things. Fes BA, the joint distribution of the error and the speed, is this marginal distribution, the marginal PDF of the speed times the conditional distribution of the error given the speed. Any problem? Now, let's remember our exponential. What is the distribution of the speed? The density of the speed. Lambda times e to the minus lambda a, right? What is lambda? 1 over 200 times e to the minus a over 200 times this thing, which is 1 over square root 2 pi a over 10 e to the negative b squared divided by 2 a squared over 100. Well, we can just write this as 50 here. So this is our joint PDF. By the way, here's a question related to 2 lectures ago. If the error is additive and the error is known to be Gaussian with 0 mean, then what is the distribution of the measured speed if you know the actual speed? So conditional on the actual speed being A, what is the distribution of the measured speed? The measured speed is actual speed plus the error, right? But the measured speed, so actual speed is fixed at A, and the error is Gaussian. What happens if you add a constant to a Gaussian? You get a Gaussian whose mean is shifted by that constant. So the conditional distribution, let me write this down. So m is the measured speed, and m is given by the actual speed plus the error. Okay? Error is Gaussian. So fm given fm given S, m given A is a Gaussian whose mean is shifted to A. 1 over square root 2 pi, the variance doesn't change, A squared over 10, A over 10, e to the negative m minus A squared divided by 2A squared over 100. Okay, so the only thing that changes is the conditional distribution, the conditional density of the measured speed given the actual speed is a Gaussian. From this, I can easily find the joint PDF of the speed, real speed, and the measured speed by Fs of S times F m given S m given A. How about that? Any questions? This one? This? This one. Okay. Now, the measured speed given the actual speed. Given that the actual speed is A, the measured speed is A plus a Gaussian. Okay? A plus a Gaussian is a Gaussian whose mean is shifted by A. That's it. Let's switch to the next example from the world of fantasy fiction. Okay? So, this is about a boy magician named Harry. So, Harry's magic wand breaks at a random point, located at a uniform position across the length of the stick, which is 40 centimeters long. Suppose the piece of the stick that Harry is left with is X centimeters long. Unfortunately, the next day, the part of the stick that's remaining is accidentally burned while casting a spell. Okay, so after this accident, the length of the stick is reduced to D, where D is uniformly distributed between 0 and X. Find the density of the remaining length of the stick. So what happens in this problem? Originally, we have this, this is the end of the stick that Harry is holding in his hand. and the stick is 40 centimeters long. Okay? Well, what happens is it breaks at some point, randomly and uniformly chosen from 0 to 40. Okay? And the remaining, length of the stick after this breaking is a random variable x. What is the distribution of x? X is uniform, right? X is uniform because it's uniform. The point of breakage is anywhere from 0 to 40. Okay? So x is uniformly distributed from 0 to 40. Okay? Then, unfortunately, one accident follows the other, and the next day, part of the stick is burned off. Okay? How much is burnt off is again uniform. Okay? So the remaining amount of the stick is y. Okay? Y. Y is distributed uniformly this time. I mean, given x, on this day we started by a stick whose length was x. Given x, y is uniform from 0 to x. It's called d in the question, but let's keep it as y for now. Or maybe switch to d. Let's switch to d. D is uniform from 0 to x. Okay, so what is fd of d? The marginal distribution of d. What do we have? We have the conditional distribution of d. We know that fd given x, small d given script x, is what? It's uniform, right? It's uniform, so it's a constant when d is between 0 and x, and the value of that constant must be 1 over x. Okay, if you plot it, 1 over x, f d given x, d given x, constant. Okay, we need to find the marginal. How can we do that? Well, let's see. When you multiply fd given x by fx of x, fx of x, what do you find? You find the conditional. I'm sorry, you find the joint density. And then you can integrate the joint density over all x, which I would like you to pay attention to is like using the total probability theorem. So let me write this again here. This is f x d x comma d times, well, integrated over all x, right? I can find the marginal by integrating the joint over all x, minus infinity to infinity. I don't care what the actual region is because I've written it in the more general way, Now, pay attention to this. I can write this as fx of x times f d given x, d given x, dx. What am I doing here? maybe it's better if I write it the other way. F d given x, fx of x dx. Do you remember what we keep doing when we apply the when we apply the total probability theorem? If we know the value of x, here is the distribution of d. Now, weigh that by the probability that x takes that value and sum over all x. This is very similar. Instead of summing, we're integrating. So, now fd given x. Fd given x is 1 over x, provided d is between 0 and x. Okay? And fx of x is what? 1 over 40 dx. Okay? The range of x goes from d2, right, 40. Because given that the remaining amount of the stick is d, okay, the values of x go from d to 40. And, okay, so this is 1 over 40 times the logarithm of x, natural log of x, 40 to d, and you can compute this as natural log of 40 minus natural log of d divided by 40. Okay, so basically we found the marginal density of d by integrating the joint, which we found by multiplying the marginal of x, which was given to us in the problem, by the conditional density of d given x, which was also given to us in the problem. And we derived the distribution of the remaining length of the stick. All right, we'll take it from here next time.